Hi guys, in this video I'm going to talk about the Gauss-Newton method, and this method helps solve nonlinear least squares, and it's basically a generalization of the Newton method, which I'll go over also in this video. And there's two ways to look at it as a generalization. One is that it kind of approximates the Hessian in the Newton method. And another way to look at it is as if it's approximating the actual function, which is nonlinear, in a linear way. So we're going to go over all the mathematical theory, and then I'm also going to show you some code in Python, and I'll also leave the code in the description of the video. Okay, so what is nonlinear least squares? Well, nonlinear least squares is when you have some response variables, some y's, and they are related to some predictor variables, some x or covariates, but the function is nonlinear in the terms of the betas. So a linear in the terms of the betas would be, for example, y is equal to beta 0 plus beta 1x. Yeah, this is linear, but it still stays linear even if I do beta 2x squared. The x's are not important, the betas are important, but it becomes nonlinear if, for example, I do beta 0x divided by beta 1 plus x, then this function is already nonlinear. Yeah, and so you get data from this, and the data is of course not a perfect fit. There is some noise, there is some noise value, and you try to find the betas, you try to find the coefficients that minimize the loss. And what is the loss? The residuals. Okay, so you look at the residuals, you look at the yi's minus the function, and you try to fit the function that minimize the squared residuals. So this is you define a loss function. The loss function is the residual squares and the sum of them over all the observations you have, and you want to minimize that function with regards to the coefficients that you can control. So you can see that the function, as I mentioned, is in this case nonlinear. And so the method of doing this with least squares is called nonlinear least squares. And you can see that this is least square because we're trying to find the betas such that the squares of the residuals will be minimized, will be the least as possible. So this is least squares. Okay, so what would you do generally if you want to find the betas? Well, you take the derivative and you equate it to 0. But again, because this is nonlinear with the betas, then the system of equations you get is no longer linear, and you don't get a closed form solution. So it's not really a problem because you have methods that manage to solve it anyway numerically. One of these methods is the Newton-Raphson method or the Newton method. So what is the Newton method? It's an iterative method, and you start with an educated guess as to where is the betas are, and you try to improve it with each iteration. So what the Newton method gives you is a way to find a root of a function. So let's say you have a function f, which depends on a variable x at time step t. Then you improve x at t plus 1 by taking the original xt and then subtracting the function at this value divided by the derivative, the gradient at this value. Okay, but this will give you the root of the function, meaning the place where the function is equal to 0. So what do you do if you want to find the minimum or the maximum? Well, you just move everything up one derivative. So the root of the derivative is the minimum or the maximum. Yeah, so you do exactly the same, only you do it with the derivative is in the numerator and the second derivative in the denominator. And of course, this can also be generalized to functions that take more than one value, like functions that take a vector of values. Yeah, so if your f is mapping from some r of p to r, then this still works. The only difference is that this will be a vector now, a vector of derivatives, and the second derivative will be the Hessian matrix. Okay, and you take the inverse of the Hessian matrix. Okay, so this is Newton method, but sometimes calculating the Hessian is complicated, and this is where Gauss-Newton method comes into play. So one way to look at the Gauss-Newton method is as an approximation of the Hessian matrix. Okay, you don't want to calculate the Hessian, so you do an approximation of it. How do you do the approximation? Well, let's look. If we take the gradient and look at the beta j position, the beta j derivative of our loss function, of our target function L, then what is it equal to? Well, remember, the loss function is just the sum of Ri squared. So the derivative with regard to beta j will be just the sum of 2Ri times the partial derivative of Ri with regards to beta j. Okay, but what is Ri? Remember that Ri is just yi minus f of xi. And xi depends on the betas. So if you take the derivative with regard to beta j, this does not depend on it. So all you get is minus the partial derivative of f with regard to beta j. Okay, so this is what I wrote here. And if you look at it, well, the minus 2 stays, but in general, if you look at it, not just in beta j, but the general derivative of L, the general gradient of L, it's equal to minus 2 times the Jacobian matrix of f with regards to beta times the vector of residuals. And what is the Jacobian? Well, Jacobian is just a matrix where in the first row, you take the first observation and you take the gradient of the first observation with regards to all of the different coefficients. So with regard to beta 1, beta 2, etc., until let's say we have p coefficients and the derivative with regards to beta p. And in the second row, it's for the second observation and so on until eventually you do it for the last observation. Yeah, and you can verify it, for example, if you take this matrix transpose and you take, let's say, the first row of the transpose matrix, multiply it by r, you will get the derivative with regard to beta 1. If you take the second row, you will get the derivative with regard to beta 2, etc., etc. So this is indeed, this equality holds. Okay, so this was the gradient, but we also need the Hessian. We also need the second derivative. So let's look what happens, say, if we take the second derivative with regards to beta j and beta k. So this is the expressions we have, this thing over here. And we need to now differentiate it again with regard to beta k. Okay, so we do it with the product rule, So it's the derivative of this expression with beta k times this, plus this times this, the derivative of this time with regards to beta k. Okay, so what is the derivative of Ri with regards to beta k? It's this term over here, Remember again, Ri is just yi minus f xi beta. So again, it will be just the derivative of fi with regards to beta k. And this will be the same. And in the second position, Ri doesn't change, and we get this expression. Okay, so what does the Gauss-Newton method says? It says this term, this expression is too complicated. Let's just put this as 0 and approximate it just with the first term. So if we approximate it just with the first term, well, the minus and minus cancels, and we are left with this expression. And what is this expression? Well, you can also verify that this is the Jacobian transposed times the Jacobian. And this is what the expression means. So now we plug this approximation. This is the regular Newton method, and this is the Gauss-Newton method. We now approximate it with what we have. So what we have this for the Hessian and this for the gradient. Okay, so the minus and minus cancels, we get a plus. The 2 here is inverted, it becomes a half, so it cancels with the 2 here. And we end up with this expression over here, which is the formula for the Gauss-Newton method. Okay, this was one view of it. We can also look at it from another perspective. We can say, instead of approximating the Hessian, let's approximate the actual function. So our function is nonlinear, but we can do a first order Taylor approximation of it, meaning a linear approximation of it, around the point that we have right now. Okay, so what we will get is that the function is approximately the function at the location of the current known coefficients, plus the derivative of the current known coefficients, the real betas minus the current known coefficients. Okay, so we can also approximate the residuals. So the residuals is this. So instead of this, let's put the first order approximation, and we will get this. Okay, and okay, let's now call these the new yi's, yeah, the new response variables, or also we can call them the working yi's, or the working response. And this, let's call this our xi's, okay, our xi tilde, okay, and this will be our new coefficient, okay, our working coefficient, working response, working predictors. And now our I is approximated by this expression over here. Now this is known because at time t, we can calculate this function at time t. So this is known, it's just some numbers that are known. The xi's are also known. The betas are what we are trying to find. And what is this expression? Well, this expression is a linear expression. So we want to minimize this approximation of the residuals. But this time it's ordinary least squares, because with regards to this representation, then we get that our new betas are linear. Okay, and this is because, again, we approximated the function with a linear function of it. Okay, so what we want to do, we want to minimize this function, the second norm squared. Okay, and what is x in this case? Well, the xi's were the derivative of fxi with regards to all of the parameters, all of the coefficients. So x is just our Jacobian matrix from before. Okay, so we already know how to solve ordinary least square, and the solution for the betas is just this expression over here. Okay, because we replace x with this Jacobian matrix. And what is the yi tilde? Well, yi tilde is just yi minus the value, the function value at the current known, current guessed parameters. So it's basically just the residuals at time step t. Okay, this is the same thing as the residuals here. It's exactly the same thing. Okay, so, and what is this beta tilde? It's just beta minus beta at time step t. So we get this expression over here. And if we take this to the other side and we say, okay, each iteration of this algorithm improves and gets us closer to the real beta, then we get, again, this same formula as before. Okay, and you can see this is exactly the same formula as before. Okay, so let's have some examples with Python. I have here a 1D case, and I have a function that is of the form a times x divided by b plus x, and our coefficients are a plus b. This is what we're trying to find. And notice that we are narrowing just to this function. So nonlinear least squares, you have to assume what is the structure of the function that you are trying to approximate the coefficients for. So in this case, the functions are of the form some coefficient times x divided by some coefficient plus x. Okay, and let's say we have some data, we are generating a data. We take the x's to be from 0 to 5, and we fit the y's according to this function, plus some noise. Okay, and if we show how it looks, then it looks something like this, okay? Okay, and now we have to calculate the Jacobian, and the way I'm doing this is numerically. I And here I do it for a function which I know that only has two parameters, a and b. And I take the function and add a little bit for the first parameter and subtract from it the same function where I subtract a little bit from the a parameter, and I divide it by 2 times the epsilon that I'm adding and subtracting, and this is a numerical approximation of the gradient. Okay, and here I do the Gauss-Newton, and I'm starting from some value that I'm giving to it, and then I'm calculating the Jacobian, I'm calculating the dy's, and then I'm just doing exactly the formula that I've seen before. So J transpose J invert times J transpose and the new y's, yeah, the dy's. And here I will run it for the first function that I mentioned with, let's say, the data that I generated. And let's say that for the first parameter, I give it 5, and for the second parameter, I give it 2. I give it some tolerance of 10 to the power of minus 5. And I tell it the max iteration is 10. Okay, so it will run. It fitted the model, and now I have the coefficients that I wanted, the a and b. And now I can calculate what would be the expected y given that my function has these coefficients. Okay, and if I do this and now I plot the same data as before plus the function that the model gives me, I will get this graph over here. So we can see that indeed it seems to fit pretty nicely to the data that we have. Okay, and we can do another function. In this case, I took a normal Gaussian function, considered the first parameter to be the mean, and the second parameter to be the variance of this function, or the mu, the location, and sigma square is the scale of this function. And I calculate the y's using my real function has a mean of 2.5, a mu of 2.5, and a sigma squared of 0.5. And I add again some noise to it. And if I want to see how it looks somewhat like this. And again, I can fit with Gauss-Newton, I can fit the model to the data, and I will get the estimated coefficients. So I give it the same data as I calculated here, some initial guess, yeah, and I plot it, and you can see it works nicely. Okay, we can also do a 2-dimensional case. Yeah, x doesn't have to be just 1-dimensional. X can be more than 1 dimension. So here I have another function that I calculate, and this time x has 2 dimensions, but I still stay with 2 parameters. And I calculate the y for the values of the function in a grid of between -5 and 5, and I scatter it. Okay, so you can see here, this is how the data looks like, plus I added some noise. Yeah, and now I will fit the Gauss-Newton to it. Now you can see the data that was given before, plus the fitting function. So you see the points are the data, but this graph over here, this contour graph, is the function that we fitted to this data. And you can also have a more general Jacobian where I don't limit the number of coefficients that the function has. This is the implementation if I take a more general implementation. Okay, and I can do exactly the same function as before, only add a parameter. And if I use the same data as before, this extra parameter that I've added will be 1. And I give it some initial guess. You can see that it gives a very similar result. The original function was 5 for the first parameter, 4 for the second parameter, and 1 for the third parameter. And we see that it gives 1 for the third parameter. And also, of course, you don't have to implement everything from scratch. SciPy has this algorithm already implemented. The only thing you need to do is to define a function that gives the residuals. Okay, and then once you have a function that gives the residual, you give that function to the least squares function with some initial guess and the extra arguments with the data. And you can see it gives exactly the same results as our manually created algorithm. Okay, so I hope you enjoyed this video and see you in the next one.